Hello everyone, today we are going to present the big data project, the music recommendation based on KKBox. We have talked about the motivation before, which is basically the um, want to do some music recommendation, and our data is from KKBox, which is a music app mainly based in Hong Kong and Taiwan. So on our data, we have the user listening activity, which means we have the user and song pair. And if there is repeating listening actions, we will target as 1, otherwise 0. And we also have the user information and song information, such as artist and the language. We use several different methodologies, such as song to WAC or SVD, to complete the prediction. For song to WAC, it's generalized from a model in NLP called word to WAC. So it creates some dense vectors for word. So for word, so maybe a 100-dimension vector, and the word with similar meanings will be closed in the vector space. And there is a word analogy, which means the vector of France minus Paris will be equal to China minus Beijing. And so why does the model works? It's unsupervised, and it's used a central word to predict the word surrounding it. So it learns from the context, and words which have similar neighbors will be similar. And we can get the word vectors from the first connecting weights of the first connecting layer in the model. So how about constant to WAC? Could we just use the play key as the context, and we use the input of a song to predict the context? So we use in our case, we use the listening history. We can also use the playlist if we have the data. And in our case, we define the session by the change of source system tab. So it's a feature given in the dataset. So it measures how the user listens to the song. So maybe from discover or library or a search. So if they change to another source, we define that it goes to a new session. And here let's look at the result of the song track. So we can calculate the cosine similarity and find similar sounds for song. So for Sunny Day, right, it's a song from J. Joe, and it's followed by some other songs from J. Joe, and also there's a song from JJ, and basically it's mainly about like love songs from Taiwan. And for the songs Mountain South, it's a folk music in mainland, and it's followed by some other songs such as Mrs. Stone. I hope some people have listened to it before, right? And basically it's more like it's in mainland, some folk songs. And for the 21 Guns, it's followed by some English pop rock. And for the Yellow Submarine, it's by Beatles. So it's followed by some more like jazz and Britain rock songs from early ages. And let's look at the artist to WAC. So we average the songs vectors of artists and use statistics to create a 2D visualization. We find for J. Joe and JJ, they were very close, right? And for Feng Wang, it's quite close because they are all big guys. But Feng Wang is in mainland. It's about some rock, so it's not so close. And for some songs like Galler and Song, they're close in the certain area. And for some Japanese, it's distant, but not so distant because this guy is about light music, and it's still very popular in the East Asia. And for some English singers, you can see the Coldplay is very close to Ed Sheeran, right? It's intuitively correct, right? And those who listen to these guys may not listen to Lady Gaga, right? Also, they are all in English.
可以拿背着就坠下去。Okay. So which just talk about the first part of our feature generation, which is sound to back, and I'm going to talk about the second part, which is converting our raw features into conditional probabilities. So currently, our raw features are mainly textual information, such as what's the song name, what is the artist name, what is the composer name, and so on. And then we have 7 million data points, and each row is basically is indexed by username and key pair. So how do we actually convert this textual information into the numerical information, and also how do we utilize this huge amount of data information? So we come up with this idea of using the conditional probabilities to first we select a subset of information based on a certain condition, and then we compute the conditional probabilities given the subset. So in that way, we believe we effectively and efficiently utilize the information, the huge amount of data rows we have, and also we convert our textual information into the numerical information. One example can be given the user ID equal to XX, or given the general ID equal to YY, what is his probability of listening to this general type of song in the past? And also, for each individual raw feature, we do a one-by-one conversion. It can be based on the users, can be based on the location, or can be based on the platform patterns. So after we come up the conditional probabilities, we use 3 different methods to test the significance of the features. The first one is random forest importance scores. As you can see, across the board, the scores are pretty close. So our first assumption is that we want to preserve all the features. And then we further test this assumption by using logistic regression. And as you can see, the t-stats of each coefficient is highly significant. So this also confirms our assumption. And finally, I do logistic regression with L1 penalty, which is pretty similar to the concept of lasso regression. And as you can see, the coefficient is also non-zero. So all these 3 methods confirm that each conditional probability feature we generate through one-by-one conversion from the raw features are useful and significant for the model prediction.
Okay, so up to now we have the normal features and the sound-to-load features. So to make the best use of the data sets, we want to also know the random factors, which is the random feature, which suggests the interaction between different users and different songs. So we use 2 matrix factorization methods. The first one is I'm sure everybody knows it. The second one is SVD. So SVD is like we have huge data sets. The rows is the user ID and the column is the item IDs. We want to decompose this into 2 small feature metrics. The first is the U matrix is the latent feature for the users, and the V vector is the latent feature for the songs. So we have the user ID column and song ID column. So the target here is the score we want to use. So the right figure is the output of the LS methods. We can see that as the dimension of the factors increase, the performance goes worse. So the best dimension of the factor is 5. So we also compare 2 different methods. You can see that the LS method outperforms the SVD, so it is used for us to extract the factors. So this is the final feature we want to use. We combine the user feature, the song features, and the predicted scores. So we have the 41 dimensions features in total.
Okay, so finally we use the XGBoost to do the prediction, and we have now 3 feature sets: the normal features, which is the conditional probability, and latent factors, and the vector features. And we test the combination of different features, and we find based on the normal feature, if we add latent and the vector, we can both get some better performance, and it's the best with the other feature sets. And here's some further research. So for instance, we didn't do any parameter tuning, so the accuracy is not very high, but we can focus more on that. And also we can also add some the light source as a global context in a session, which is learn from Airbnb. What they did is like they use a listing ID as a global session in the context, and we can also try other different models, and also we can consider more on the system design. So thank you.